The very fabric of our built environment. We are going beneath the concrete, past the plastic, and into the fungal kingdom to explore how mushrooms are set to become the building blocks of a sustainable future.
That's right. We are peeling back the walls of modern construction to ask a really crucial question. What if the solution to our massive construction waste problem was literally growing in the ground?
Right.
Mycelium-based composites, or MBCs, are the answer. And they represent, a profound shift away from the fossil fuel-intensive production models that define architecture today.
Okay, let's unpack this. Our source material today is exceptionally dense. We're looking at cutting-edge research from European labs, specifically some German development documents detailing material optimization.
And some highly specific production patents, which are fascinating to get into.
Yeah, and comprehensive architectural case studies. So our mission is not just to summarize this material, but to truly understand the chemistry, the precision engineering, and frankly, the economic hurdles involved.
Exactly. We want to show you exactly how this innovative material can revolutionize construction by offering a truly circular, self-healing, and carbon-negative alternative.
So we need to start with the scale of the problem. Why do we even need a revolution in building materials? It all comes down to waste.
It really does.
When we talk about common insulation materials, the stuff inside your walls, like expanded polystyrene, EPS, or mineral wool, what is their ultimate environmental fate?
Well, the environmental legacy of conventional building materials is one of the greatest silent crises in the climate debate. When these materials reach the end of their service life, often after just a few decades, they are nearly impossible to manage sustainably.
And EPS is a huge offender.
A particular offender. It's bulky, it's chemically complex, and it's so difficult to separate from building rubble. A lot of it just ends up classified as hazardous waste.
Which means we are either burying massive volumes of petrochemical material in landfills where they will, persist for centuries, or we are burning them
in energy-intensive incinerators, releasing all that sequestered carbon right back into the atmosphere. It's a completely linear, wasteful, and resource-intensive system.
It's broken.
Exactly. We desperately need a material designed to integrate back into nature's cycle, one that doesn't just reduce its carbon footprint, but actually eliminates the concept of waste entirely.
And this is where the genius of the fungal kingdom steps in. The solution is mycelium,
which is essentially the vast root-like network of a mushroom.
This network acts as a natural, low-energy, biofabricated glue. So instead of relying on expensive, high-heat petrochemical adhesives, the fungus performs the binding work for free.
The core innovation here is leveraging nature's own recycling expert. Mycelium forms this vast, intricate mesh of filamentous strands called hyphae. We simply introduce this fungus to agricultural waste like straw, husks, or sawdust, which is essentially carbon that plants have already pulled from the atmosphere. The fungus colonizes and binds this loose, fluffy waste into a cohesive, stable composite brick or panel.
So it completely flips the script.
It fundamentally flips the script. Waste is now the raw material, and growth, not energy, is the manufacturing driver.
It's the ultimate zero-waste manufacturing process. We're taking carbon-sequestering trash and growing it into a high-performance building material. So let's get specific. What exactly is a mycelium-based composite?
Okay, yeah.
If you were to hold one of these biobricks or MBCs in your hand, what would you actually be holding? What's the official definition?
So a mycelium-based composite is precisely defined as a biocomposite. It's created by growing the filamentous hyphae, that vegetative part of the fungus, on a lignocellulosic organic substrate.
Lignocellulosic, that's the key word there.
It is. It refers to plant material containing lignin, cellulose, and hemicellulose. So we're talking about cheap, abundant, often discarded materials. Rice husks, wood sawdust, cereal straw, or even specialized things like bamboo microfibers.
So the agricultural residue is just the inert, bulky filler material, and the mycelium is this specialized biofabricated adhesive. It's replacing the need for those high-energy, fossil-based binders we are trying to phase out.
Precisely. And chemically, the structure the mycelium weaves relies on two fundamental natural biopolymers, chitin and cellulose.
Chitin, like in an insect's shell.
The very same. It's the same fibrous material, and it provides incredible tensile strength, while cellulose adds bulk and structure. The result is a structure that is both extremely lightweight, which is key for logistics, and surprisingly robust.
So moving up to the systemic level, this material is a massive engine for the circular economy. We are fundamentally changing waste economics.
Absolutely. Think about the scale. Agriculture generates these vast waste streams, often burned or left to rot. MBCs convert this residue, which currently costs money to dispose of, into a high-value building resource. This drives regional circularity. You can imagine an insulation factory situated right next to a rice farm, with the rice husks going directly from harvest waste to raw material input.
Let's discuss the environmental credentials beyond just waste reduction. How does the manufacturing process itself compare in terms of, energy consumption and emissions?
The credentials are far superior to conventional materials. Let's contrast MBCs with EPS. Producing EPS requires high heat, complex chemical synthesis, and petroleum inputs.
It's an industrial process.
A heavy industrial process.
Okay.
Manufacturing MBCs, conversely, is driven by biological growth. It's essentially a very controlled agricultural process. It requires significantly less energy overall, primarily for sterilization, climate control, and final drying.
And that means lower emissions.
It directly translates to drastically lower embedded CO2 emissions compared to energy-intensive industrial processes. It's carbon negative right out of the gate.
And the life cycle benefit doesn't end when the wall is constructed. The end-of-life story is completely different from EPS.
Oh, it's the ultimate closed loop. MBCs are fully biodegradable and compostable. They are specifically designed to return to the natural carbon cycle.
So when you tear a building down in, say, 70 years...
Exactly. When a building that utilizes MBCs is eventually deconstructed, the insulation material can be separated, ground up, and safely composted, where it biodegrades fully, potentially enriching the soil rather than polluting a landfill.
That sounds like a dream scenario for material science. But if the manufacturing process is basically biological growth and uses cheap waste materials, is that simplicity reflected in the cost? I mean, is this economically viable right now?
It absolutely is. Manufacturing costs are considered relatively low. The major cost input is typically energy for climate control and sterilization, but the raw material, the substrate, is extremely cheap.
So it's most viable when it's local.
The viability is strongest when manufacturers utilize local, readily available waste substrates like straw or sawdust. This eliminates complex international logistics and the high volatility of commodity prices tied to petroleum, providing a stable, localized, and resilient supply chain.
We mentioned that the mycelium is the glue. Which specific fungal species is the true workhorse of this biofabrication process?
The oyster mushroom, Chlorotis astratus, is the most highlighted and commonly used species. It's selected because it's a vigorous grower and imparts excellent mechanical properties to the final composite.
Are there others?
Oh yeah. Other effective species include Trametes multicolor and Fomes fomentarius. Researchers are constantly experimenting, selecting species not only for speed of colonization, but also for the specific density and fire-retardant qualities their cell walls provide.
So let's walk through the basic production process. If I were a listener wanting to visualize how this happens in a factory setting, what are the, say, 5 or 6 key steps?
The process is elegant in its simplicity, but it requires great precision. It starts with preparation, where the lignocellulosic substrate is sourced, cleaned, and often chopped or milled to a consistent particle size.
Because you have to make sure you're only growing in the mushroom you want, right?
Exactly. That leads to the critical second step, sterilization or pasteurization. This is a high-heat treatment applied to the substrate to eliminate all competing microorganisms, like unwanted bacteria or molds, which could ruin the batch.
Then comes the fungus itself.
Step 3 is inoculation. The sterile substrate is mixed with the mycelium spawn, the biological starting culture. Step 4 is filling molds containers, which defines the final shape of the panel or brick.
And then step 5 is the magic.
Step 5 is the magic. Incubation. This is the growth phase where the mycelium colonizes the substrate for typically 2 to 3 weeks in a controlled, dark, climate-specific environment, binding it all together.
And the final, crucial step, stabilization.
Step 6 is drying. This is the point where we stop the biological process. The material is dried at a minimum temperature of 60 degrees Celsius. This temperature is vital because it halts the fungal growth, killing the living cells, and ensures the product is stable, dormant, and won't resume growth or decompose when you place it inside a wall.
It's essentially flash baking the biological scaffolding into a permanent structural form. It seems almost too simple, which is perhaps why it's so powerful.
It is.
Simplicity is great, but performance is paramount. When we put an MBC block next to a piece of expanded polystyrene, how do they stack up, starting with thermal insulation?
The performance metrics show that MBCs are not just a sustainable substitute, they are a direct competitor, and in some ways superior. In terms of stopping heat flow or thermal conductivity, MBCs are highly competitive.
What are the numbers?
Their average thermal conductivity is recorded at about 0.05 watts per meter, Kelvin WMK.
Let's contextualize that metric for the listener. What does 0.05 WMK mean in the world of construction?
That is the sweet spot. For reference, materials like EPS or mineral wool designed for high-efficiency insulation sit in the 0.03 to 0.04 WMK range.
It's right there with them.
Exactly. MBCs are firmly in the category of effective, energy-saving insulation. The incredibly porous, air-filled structure woven by the mycelium is what traps the air and minimizes heat transfer, just like traditional foams.
But you mentioned a superior performance area, which is the thermal buffering capacity. This is where the physics gets really interesting.
This is a huge, often overlooked architectural advantage. Thermal buffering is a material's capacity to absorb, store, and then release heat slowly. It relates to thermal diffusivity.
Okay.
And MBCs have a thermal diffusivity 2 to 3 times lower than EPS. This means they are far better at dampening and smoothing out temperature peaks and troughs.
Can you elaborate on the real-world impact of that? Why does that matter more than just a low conductivity rating?
Okay, think about a structure in a climate with major temperature swings.
Yeah.
A hot desert region, or even a typical continental environment where it's freezing at night and warm during the day. Right. A material with superior thermal buffering acts as a time delay mechanism. If the sun is beating down all day, the mycelium wall slowly absorbs that heat, delaying its entry into the interior space until late evening, or perhaps not at all before the external temperature drops again.
So rather than forcing your air conditioner to fight the heat instantly, the material itself handles the regulation naturally.
Exactly. It naturally regulates internal temperature fluctuations, maintaining a steady, comfortable environment. This significantly reduces the need for constant, energy-intensive heating or cooling systems, potentially saving massive amounts of energy over the life of the structure.
For architects designing low-energy or passive houses, this must be invaluable.
It is. It's an invaluable feature.
Okay, moving on to sound. How does the porous mycelial structure perform on acoustics?
The structure is excellent for acoustic dampening. MBCs demonstrate sound insulation properties that are actually superior to EPS.
Really? Why is that?
The interconnected, irregular air pockets within the fungal network are highly effective at dissipating sound energy. This makes them ideal for environments where acoustic comfort is crucial, like interior partition walls in high-density housing, offices, or even recording studios.
So, quieter, more comfortable indoor living.
That's the idea.
And crucially, fire safety. This is where I have to ask a challenging question. You mentioned MBCs achieve a B1 fire safety classification. Is B1 truly sufficient for widespread adoption in large-scale commercial structures, or will they always need expensive external fire barriers?
That is the right question to ask, because B1, which is classified as flame retardant, is good, but it's not the highest standard. True A ratings non-combustible are often expected for critical structural elements in high-rise buildings.
But it's better than some synthetics.
It is. B1 is still a favorable rating, especially when you compare it directly to many synthetic foams which, if untreated, can be highly flammable and release toxic fumes when burned.
So B1 means it doesn't feed the fire actively, but it's not passive.
Correct. The good news is that the safety can be further optimized. Our sources show that by incorporating inexpensive additives like rice hulls, which are highly siliceous, or even finely ground glass fines, you significantly improve the material's structural integrity under heat and its fire resistance.
So you can tune it.
You can tune it,
Yeah.
and that pushes them closer to meeting stringent codes, positioning them as a much safer and less toxic alternative to many fossil fuel polymers.
That's a strong list of strengths. But as we discussed, no material is perfect. What is the biggest material weakness that engineers are currently battling?
The major weakness is, without question, water susceptibility.
Router.
Water. MBCs are naturally organic and highly porous, leading to high water absorption and moisture vulnerability. Measurements show absorption rates reaching between 110% and almost 140% of their own dry weight.
Wow.
Yeah. And this is critical because excessive moisture not only compromises the material's structural performance, but significantly increases the risk of biological degradation and mold formation in a humid environment.
That sounds like a serious hurdle for construction, given that moisture is an inherent risk in almost all climate zones. What are the specific established engineering strategies to mitigate this water problem?
Engineers rely heavily on external and internal modification. The first line of defense is strict environmental control during installation and the application of effective external coatings.
Like a sealant.
Exactly. These can be traditional mineral coatings, which offer great weather resistance, or newer sustainable options like biopolymers or wax coatings. The second strategy is internal, using hydrophobization techniques during production, essentially treating the material to make the surface water repellent, often through specialized chemical or plasma treatments.
So we're treating the finished biobrick the same way we treat wood to protect it from the elements.
Precisely. You're protecting the biological core with a robust, moisture-resistant shield.
Finally, let's revisit mechanical strength. Can a material grown from fungus ever provide load-bearing capacity?
Not yet. Not for primary structural load bearing. Currently, their strength limits them to semi-structural and non-structural applications. Insulation, partition walls, furniture.
But the performance is impressive for what it is.
It is, especially when compared to similar synthetic materials. Compressive strength levels have been measured ranging between 387 and 562 kilopascals, or kP.
To give the listener some perspective, what does 500 kPa mean in practical terms?
That's equivalent to about 72 pounds per square inch. While that's nowhere near the 20,000 kPa of standard concrete, it significantly surpasses the compressive performance of many commercially available synthetic foams.
So they're strong for a foam.
Exceptionally strong for a foam-like material. They can handle significant pressure and are certainly robust enough to be stacked and used in internal, non-load-bearing walls.
And you mentioned the fascinating concept of tuning the material. How does the manufacturer control whether the final product is soft and foam-like or hard and wood-like?
That control is achieved through two main variables: the type of organic substrate and the post-processing technique. By varying the ratio of substrate, say, more dense sawdust versus light straw, you change the structural density.
Okay.
And crucially, the application of pressure and heat after the mycelium is fully grown is key. Without heavy pressing, it remains soft, porous, and foam-like. But if you apply significant heat pressing, you compress the material, driving out air and achieving a density that mimics cork or lightweight wood.
So you can tune the material toward a much higher strength profile.
Exactly. This tunability is absolutely vital for expanding its architectural utility.
This brings us into the laboratory where the real industrial secrets are developed. We're moving beyond the basic idea of mycelium on straw into patented processes that ensure industrial-grade consistency. It turns out that simply using traditional agricultural waste as a carrier material presents major hurdles.
That's right. Traditional bulk substrates, straw, cereal grains, wood chips, they're great for nutrient supply, but they create logistical inconsistency problems. They often produce mycelial structures that are too dense and compact.
Which slows down growth.
It inhibits uniform colonization and paradoxically can slow growth because the fungus struggles to exchange gas.
And if you use cereal grains, there's an opposite problem.
Yes. Cereal grains, if you prepare them by boiling, they become sticky and agglomerate. And even when separated, the mycelium often only grows on the surface of the grain kernel.
Which gives you a weak final product.
It leads to low overall mycelium density in the final product and requires costly, time-consuming manual separation steps before it can even be mixed with the inoculum. These inefficiencies just kill industrial scale-up.
So the patented solution is to completely change the substrate from an organic nutrient source to an inert structural carrier. This is where expanded perlite comes in.
Perlite is the breakthrough. It's a volcanic aluminosilicate rock that is highly porous and chemically inert. It acts purely as a carrier material.
What's the key advantage?
The key advantage here is that because perlite is a rigid, porous structure, the mycelium grows protected inside the perlite granules. This drastically improves inoculation success, ensures structural integrity, and eliminates the need for manual loosening.
This is where we need to dive into the molecular specifications. The research outlines four crucial, non-negotiable specifications for optimizing this inert substrate for industrial growth. What is the first specification?
The first is the anhydrous state. The substrate must be practically water-free, specifically containing less than 5 weight% residual moisture.
Why is that so important?
If the substrate is wet from the start, it promotes slower growth, creates poor final material quality, and results in low yields. Moisture control is fundamental to ensuring the fungus focuses its energy on structural growth, not competing with existing water content.
Second is low density. This seems counterintuitive for a construction material.
It does, but density must be very low, specifically less than 0.2 grams per cubic centimeter, ideally near 0.1 gc-meteron.
And that's for economic reasons.
It's critical for economic viability. If the density is too high, the mycelial growth rate slows down dramatically because of poor gas exchange, making the incubation period too long and the product economically unviable. Low density equals faster growth and a lighter product.
The third feature is arguably the most surprising in its specificity, the granule size. The research demands a tightly controlled size between 2 and 5 millimeters, preferably 3 to 4 millimeters. Why is that narrow range so vital?
This is a perfect example of bioengineering precision. The size dictates the internal geometry of the entire composite. If the granules are too small, below 2 millimeters, they inhibit gas exchange and fruiting potential because the void spaces collapse.
And if they're too big?
If they're too large, above 5 millimeters, you get inconsistent colonization. You end up with large, uncolonized pockets, preventing the uniform density needed for a reliable, predictable building product. The 3 to 4 millimeter size creates the ideal, interconnected network of tunnels and air gaps for the hyphae to colonize quickly and uniformly.
Here's where it gets really interesting, and the fourth crucial feature is porosity.
Yes, the material must have a high void volume, the amount of air within the structure ranging from 60 to 90 vents per cent, ideally near 70 vent%.
It's mostly air.
It's mostly air, and that air content is absolutely vital. Mycelial growth is an aerobic process. It requires constant oxygen and releases CO2. If the porosity is insufficient, the fungus essentially suffocates itself, leading to patchy growth or failure. The perlite selection ensures this critical void volume is always present.
So the perlite provides the perfect structural framework, but the fungus still needs nutrients to grow. That shifts us to the precise fungal diet, the liquid nutritive phase that the perlite absorbs before inoculation.
This is where the chemists formulate the perfect biological growth accelerator. They leave nothing to chance.
So what's in the recipe?
Let's look at the carbon source. Dextrin is favored over pure glucose or starch.
Why dextrin? What's wrong with simple sugar?
Dextrin is essentially a pre-digested hydrolyzed starch. It is favored because it is directly and immediately assimilable by the fungus, saving the fungus metabolic energy it would otherwise spend breaking down complex starch. Moreover, simple glucose creates extremely high osmotic pressure, which stresses the fungal cells, leading to slower, weaker growth. And native starch forms a sticky, hard paste during the required high-heat sterilization process, making the substrate unusable.
So dextrin avoids all those problems.
It avoids all these processing and biological problems.
And for building the fungal structure itself, we need proteins and nitrogen.
Those are supplied via amino acids, typically sourced from plant protein hydrolysates like soy proteins. The research is explicit that a full suite of specific amino acids is required for optimal health and rapid structural growth.
Like a protein shake for mushrooms.
Pretty much. They list alanine, arginine, glutamic acid, lysine, proline, and many others, a total of around 15 specific amino acids. These aren't just food. They are the immediate structural building blocks needed to rapidly synthesize the hyphae walls and internal machinery, ensuring maximum density in the composite.
Now, let's talk about the protective agents. Fat and vitamin E. The research mandates the inclusion of polyunsaturated oils, like soybean oil. What is the role of tocopherols, the vitamin E carriers, in the fungal cell?
This is a critical metabolic detail for long-term material viability. Tocopherols, which are vitamin E carriers, are crucial because they serve as powerful antioxidants. They strengthen the defense mechanisms of the fungal plasma membrane, the cell's boundary, minimizing cell aging and protecting the cell from oxidative stress that occurs during rapid growth.
It's like giving the fungus a potent structural supplement to ensure its cell walls are robust and resilient.
Exactly.
And those oils aren't just passive supplements, they actively turn on certain metabolic pathways in the fungus, right?
Yes, this is the crucial activation step. The presence of these specific polyunsaturated oils activates the fungus's own liposes and phospholipases. These are digestive enzymes.
So it preps the fungus.
By turning on these enzymes, the fungus is metabolically prepared or trained to break down the similar complex energy sources that exist in the bulk substrate, the straw or sawdust, later on. This metabolic preparedness accelerates the subsequent colonization phase when the fungus encounters the full lignocellulosic waste matrix. It speeds up the entire industrial process.
So we give it a perfect liquid diet and a perfect structure, and we activate its internal machinery. What about the inorganic factor? Calcium.
Calcium oxide is added because calcium plays a pivotal role in cellular energy transport. Calcium activates adenosine triphosphate, or ATP, the core energy currency of the cell.
So it's an energy booster.
By ensuring optimal calcium levels, the process maximizes nutrient uptake across the cell membrane, providing the high energy necessary for the rapid growth and cell division needed to form that incredibly strong networked mycelium.
This precision recipe really underscores that this is not just agriculture. It is true industrial-scale bioengineering, controlling natural growth cycles with microscopic chemical detail to achieve predictable, high-performance structural results.
It absolutely is.
We've established that MBCs are strong contenders for insulation and acoustic paneling, but the true excitement comes from their versatility. We're seeing them replace wood, foams, and plastics in a dizzying array of diverse products.
The adoption curve is accelerating in non-construction sectors first. They are replacing traditional materials in complex, molded packaging, think high-end electronics packaging, and moving into household items and furniture design.
Why there first?
It's driven by the fact that you can grow the material directly into a specific mold, eliminating significant machining and waste.
And there's an alternative fabrication method that eliminates the agricultural substrate altogether, creating a different kind of material entirely. Pure mycelium.
Yes, this involves growing mycelium in a static liquid culture instead of a solid substrate. The fungal filaments form a dense, robust mat on the surface of the liquid.
And when you dry that,
When this mat is harvested, processed, and dried, the resulting material is dense and flexible, resembling leather or thick paper. This pure mycelium is the source of bioleather being used in fashion, apparel, and high-end accessories, further demonstrating the material's range.
moving back to architecture, the adoption often begins with experimental, high-profile structures that prove the concept. What are the key case studies that have shown the potential of mycelium construction?
The most important early example was the Hi-Fi Pavilion built at PS1 in New York in 2014. This structure was designed using open-air bricks grown entirely from mycelium. It successfully showcased the material's strength, even without external cladding, in a temporary setting.
And what made it so powerful was the public interaction.
That's right. Visitors could touch the bio-bricks, see the material, and understand that it was grown, not manufactured.
And its end of life was integral to the concept.
Absolutely. When the exhibition closed, the pavilion was composted, proving the material's circularity in a highly visible way. Another crucial example highlighting localized production is the growing pavilion featured during Dutch Design Week.
And that one used local waste, right?
This structure utilized agricultural waste sourced exclusively from surrounding farms, demonstrating the practical reality of hyperlocal material supply chains.
Current research seems heavily focused on getting MBCs into the structural fold. Even if they aren't carrying the full load themselves, they are focusing on hybrid structures.
This is the critical next step toward widespread adoption. Researchers are combining mycelium composites with load-bearing structures, often using 3D-printed, computer-generated wooden lattice frameworks.
So the wood is the skeleton.
The wooden lattice provides the necessary engineered, predictable structural stability, the high TRL component. The MBC is then grown around or within this lattice.
Why is this hybrid model necessary rather than just trying to grow stronger bricks?
It's about maximizing strengths and minimizing weaknesses. Wood or engineered timber handles the compressive and shear forces needed for a multi-story building. The MBC, which is grown directly into the voids, then provides the CO2-neutral, circular interior fittings, maximizing its superior acoustic dampening and thermal buffering properties.
So it's not asking the mycelium to do something it can't.
Exactly. It's a pragmatic approach to immediate adoption.
Beyond function, the concept of a material that inherently decomposes has inspired artists to make powerful sculptural and existential statements.
The material forces a confrontation with permanence and impermanence. Look at Zach Landsberg's full-scale sculpture of Christopher Columbus. This piece was designed to slowly, visibly decompose over 3 months.
Which is a statement in itself.
By using a bioregenerative material to depict a figure tied to conquest and resource extraction, it delivered a profound critique of colonialism and permanent monument construction, celebrating regeneration and the natural cycle.
It's a conversation about life cycles and death that traditional materials like bronze or marble simply cannot facilitate.
And that philosophical perspective is translating directly into practical products for eco-friendly burial. The development of burial suits and living coffins that use mycelium is directly tied to the idea of a material that facilitates decomposition.
How does that work?
Mycelium helps rapidly and safely break down the body, facilitating a quicker, cleaner return of the body's nutrients to the soil in an environmentally benign way.
Given the simplicity of the basic processed fungi on waste, it has naturally spurred a grassroots movement.
Yes, the democratization of the material is fascinating. The process is accessible enough to support a robust grow-it-yourself or GIY movement. Designers, students, and hobbyists can purchase, spawn, and experiment with custom molds for small-scale products, furniture prototypes, or art pieces.
And that grassroots innovation is crucial.
It really is rapidly pushing design and application possibilities forward faster than centralized R&D labs could manage alone.
The science and the design are compelling, but for MBCs to truly replace high-polluting conventional materials, they must scale up economically. What is the current maturity level, and what are the major hurdles to industrial adoption?
The commercial reality is that the technology readiness level, or TRL, is still low to moderate, measured between TRL 3 and 7 across different products.
Let's define TRL for our listener. What does TRL mean in this context?
The technology readiness level is a metric used to assess the maturity of a technology. TRL 1 is basic research. TRL 9 is a system proven in an operational environment, fully commercialized.
So TRL 3 to 7 means we're still in the development phase.
We're past proof of concept and prototype testing, but not yet fully optimized and standardized for mass production. We are still in the phase of iterative scaling. Full marketability and deep integration into the construction sector are estimated to take another 5 to 10 years.
And that requires investment.
It requires extensive patient capital investment to bridge that gap from TRL 7 to TRL 9.
And the regulatory environment must be a massive bottleneck for any novel material entering the conservative world of construction.
Standardization and certification are the crucial non-negotiable steps. Architects and large construction companies operate on razor-thin margins and zero-risk tolerance. They need independently tested, certified, and repeatable performance metrics for fire safety, structural integrity, and long-term durability.
And that takes time.
It's a lengthy, rigorous process that currently limits MBCs to smaller projects or non-structural roles.
And economically, they are fighting an uphill battle against materials whose true costs are subsidized by the planet.
That's the key economic disadvantage.
Yeah.
MBCs compete with materials like EPS, where the true environmental externalities, the cost of CO2 emissions from production, the financial burden of landfilling plastic waste, or the health impact of toxic components are simply not factored into the market price.
So if there was a true carbon tax,
If every ton of embedded CO2 or every cubic meter of landfill waste came with a true cost, the economic argument for MBCs would become immediately compelling, driving rapid adoption. Until then, they rely on subsidies or consumers willing to pay a green premium.
let's switch gears to the structural integrity needed for long-term use, bringing up that fascinating concept we touched on, the longevity conflict. How do you achieve 100 years of durability with a material that is, by its very nature, biologically degradable?
This is the core engineering challenge. MBCs must guarantee structural stability for the expected lifespan of a building, often 70 to 120 years, yet remain fully biodegradable upon demolition.
So how do you manage that conflict?
It's managed through effective shielding. The mycelium core, designed for biological recycling, must be protected by highly effective, sustainable mineral or non-biodegradable external coatings. These coatings must be durable, weatherproof, and designed to last for decades, ensuring the longevity of the structure while preserving the biomaterial inside.
And what about the inherent biological risks that you must manage? We are talking about fungus in a wall. How do you guarantee safety from mycotoxins or insect attraction?
These risks are managed proactively through careful selection and control. Fungi species can potentially produce harmful mycotoxins, so mitigation relies on strict strain selection, ensuring only certified non-toxic species like many pleurotus strains are used.
And bugs.
Second, organic materials attract insects, so external coatings must include insect and mold repellents. Future solutions are exploring genetic modification to enhance the fungi's inherent resilience against pests and decay without relying purely on chemical treatments.
It all comes back to control.
Maintaining strict environmental control and pH levels during the growth phase is also key to preventing undesirable molds from colonizing the material prematurely.
Regarding production logistics, the idea of growing materials can sound land-intensive, but is this actually the case for MBCs?
Surprisingly, no. Unlike traditional agriculture, which requires vast fields, MBC production can be scaled vertically.
So you can do it in a factory.
Because the process requires controlled climate and sterilization, it is ideally suited for highly productive multi-story industrial halls. This allows manufacturers to utilize existing industrial zones or brownfield sites, maximizing output without requiring new land conversion, which is a significant advantage in dense urban areas where space is scarce.
If we connect this to the bigger picture, the sheer scale of the construction industry means the adoption of MBCs could be one of the most powerful tools in our climate action toolkit.
It absolutely is. MBCs qualify as a negative emissions technology, or NET.
That's a critical distinction.
It is. They are not merely carbon neutral, which
Hmm.
means they emit zero carbon during production. They are carbon negative because they sequester CO2 pulled from the atmosphere by the original plant biomass and then lock that carbon into durable construction materials for decades.
Can you quantify that carbon capture potential for us?
Based on comprehensive modeling, the potential is vast. Estimations suggest a long-term CO2 removal potential of approximately 13.518 tons of CO2 per year for every single hectare of developed area utilizing MBCs for insulation.
That's incredible. So by building a wall, you are effectively creating a temporary carbon sink.
Exactly. Over the lifespan of a building, this contributes to enormous verifiable carbon storage.
That puts the impact into perspective. Finally, what are the systemic co-benefits, the secondary advantages this material brings that benefit the entire construction ecosystem?
Beyond the carbon capture, the benefits are numerous. First, logistics. MBCs are significantly lighter than concrete or many timber products, which translates directly to reduced fuel consumption during distribution and less wear and tear on infrastructure.
And second?
Second, modularity. MBCs can be grown into specific, complex shapes, which shortens on-site construction times and reduces labor costs.
I would care about modularity if I were a developer, and I would care about reduced fuel consumption if I were a city planner.
Precisely. Furthermore, the technology encourages the utilization of invasive lignocellulosic species. We can literally create new value chains from harmful plant growth-reducing resource competition with food crops.
And what's the most futuristic benefit?
The most ambitious co-benefit being researched is the potential for self-healing composites, where the dormant mycelium could be reactivated by moisture if a small crack develops, allowing the material to repair itself structurally.
This has truly been a deep dive into the myco-revolution, revealing an extraordinary opportunity for the construction industry. We've seen that mycelium-based composites offer clear, scientifically proven strengths.
Right. Genuine circularity, superior thermal buffering capacity, and acoustic properties that lead to quieter, more comfortable living.
But the journey is not over. The technology must still overcome the high hurdle of water susceptibility, achieve full industrial scalability to bridge that TRL gap, and
And perhaps most complexly, convince a conservative construction industry and skeptical consumers to trust the sophisticated engineering provided by the fungal kingdom.
so what does this all mean? It signifies a fundamental and necessary shift in philosophy. We're moving away from the paradigm of resource-intensive, high-heat, high-waste production toward biofabrication.
We are learning to harness the networked, collaborative, and intelligent power of nature's own recycling experts.
Right.
And given that the foundational technology exists today, with specific patented recipes and robust performance metrics to grow safe, environmentally superior building materials from literal agricultural residue, the biggest hurdle may no longer be technological development.
What is it then?
It may be the speed at which regulatory bodies, investment firms, and the vast construction industry can be trained and convinced to move beyond their legacy systems and fully trust the biological intelligence that built this planet.
It makes you wonder, if we can grow our walls from mushrooms, what else have we overlooked? Thank you for joining us for this deep dive into the future of building materials.